In this video, we're going to discuss entropy and the second law of thermodynamics. But first, a brief introduction. When we discuss entropy, we venture into an area of physics that is a bit more abstract. Entropy involves the direction of time, as well as how a physical process proceeds. Time moves in one direction, as does an irreversible process. Entropy helps to describe why a process is irreversible and how it proceeds. Previously, for an ideal gas, we looked at the kinematics of individual molecules. However, entropy is a measure of the system as a whole, not of individual molecules. In fact, entropy is another property of the state of a system, along with pressure, temperature, volume, energy, and mass. One definition of entropy is the measure of randomness or disorder of a system. In nature, most processes are irreversible and proceed from less disorder to more disorder. Examples are heat loss to friction from sliding, milk diffusing in a cup of coffee, or heat lost from a hot body to the surrounding air. All of these processes occur spontaneously and are irreversible. You will never see the reverse happening spontaneously in nature. Now we can state the entropy postulate. If an irreversible process occurs in a closed system, the entropy S of the system will always increase. It will never decrease. Mathematically, we can define the change of entropy as delta S is equal to the integral from the initial to the final state of dq over T. And the units for S are joules Kelvin. As you can see, the change in entropy depends upon the temperature of the system and the amount of heat transferred in or out of the system. Also, the change in entropy depends only on the initial and final states of the system, not the path taken between them. Sometimes we can't find the change in entropy for an irreversible process. So if you have a process going from A to B and it's irreversible, often we can't actually calculate the entropy. However, we can find the change of entropy by replacing the irreversible process with an isothermal reversible process that has the same initial and final points. So if we look at a reversible process that goes like this and back like this, and you take any reversible process that's isothermal, we can find the entropy of the system. That's because the entropy only depends upon the initial and final states, not the path between them. Since entropy only depends upon the initial and final states, the change of entropy will be the same as with the irreversible process, and then we can use the equation delta S is equal to Q over T. And that's for an isothermal process. Now, if we go back to the first law of thermodynamics, which says that the change in internal energy is equal to Q minus W, we can derive the following: that the change in entropy is equal to NR times natural log of V final over the initial plus NCV times natural log of T final over T initial. And if you look at the first law equation, basically this part is related to the work done, and this part is related to the heat transferred. If we also consider reversible processes along with irreversible processes, we can modify the entropy postulate to read the following: if a process occurs in a closed system, the entropy of the system will increase for an irreversible process and stay the same for a reversible process. It will never decrease. So for this statement, we can rewrite the second law of thermodynamics as the change in entropy is greater than or equal to 0. And the greater sign occurs with an irreversible process, and the equal sign occurs during a reversible process. Now, this applies to a closed system, but the entropy can increase in one part of the system and decrease in another, thus obeying this second law of thermodynamics. The concept of entropy is used in engines and refrigerators. So let's look at a heat engine. A heat engine extracts energy from its surroundings in the form of heat and then does useful work, usually as mechanical energy. It uses a working substance to do this, for example, gasoline or steam. It goes through cycles when the system returns to its initial state repeatedly. So let's look at a Carnot engine, which is a type of heat engine, but it's a type of heat engine where all processes are reversible and there is no wasteful loss of energy due to friction, turbulence, etc. It also has the highest efficiency of any engine. It's basically your ideal engine. We're going to use the PV diagram, entropy diagram, and energy flow diagram to discuss the Carnot engine. In the PV diagram on the left, you can see the Carnot cycle, and it has 4 stages, and we'll look at each stage: A to B, B to C, C to D, and D back to A. So A to B follows along the isotherm, temperature H, hot temperature. So that's an isothermal process. And that means the change in temperature equals 0. We see that energy is absorbed. Q sub H is absorbed. So you get Q sub H is absorbed, which means that we do have a change in entropy because entropy is equal to dQ over T. So entropy goes up, and you can see that on the entropy diagram. From A to B, entropy goes up. We also have an expansion from volume V sub A to volume V sub B. So the volume goes up, which means positive work is done. Now, from B to C, we have the temperature going from TH to TC. This is actually an adiabatic process, in which case Q is equal to 0. And since Q is equal to 0, our S stays the same. We have no change in entropy. And the volume, however, goes from volume B to volume C. So that's an increase in volume again. So we have positive work again. Now let's look at C to D. That again is going along the isotherm TC, cold temperature. So that's isothermal. Delta T equals 0. And in this case, you can see that we're losing energy in the form of heat. So we have QC is lost. So since Q is going down, entropy goes down. And our volume is changing from volume at C to volume at D, which means the volume is decreasing. So there's work done, but in this case, it's negative work. And lastly, we go from D back to A for one full cycle. And that's adiabatic again, because our Q is the same. There's no increase or loss of energy in the form of heat. Our temperature goes from Tc to Th. And since Q is the same, that means S is the same. And again, our volume is going down from volume at D to volume at A. So volume is decreasing, so we get negative work again. So you can see that we have a complete cycle where heat is lost or absorbed from A to B and C to D, and we get a change in entropy from A to B and C to D. However, because we come back to A, our change in internal energy is equal to 0, and our change in overall entropy is equal to 0. And we also find that the work that is done is found to equal QH minus QC. And we can look at our energy flow diagram up here. We have our hot reservoir where heat is given up to the cold reservoir, but some of that heat does work, and therefore that work is equal to the difference in TH minus TC, the amount of heat that goes into work. And that's what that formula means. And this is the cycle of the engine that keeps going back to the same spot. So again, for a complete cycle where there's no change in internal energy or entropy of the system, we also find that QH over TH, we can use the absolute value, is equal to QC over TC. Again, the absolute value. And let's look at the net work done. If you go back to the Carnot cycle diagram, there's positive work being done from A to B and B to C, and negative work done from C to D and D to A. So our net work is the difference between the positive work minus the negative work, and that's equal to the area between the two curves as shown on the diagram, the shaded area. Now let's talk about the efficiency of an engine. Efficiency, let's call that E, is defined as the energy we get out per cycle over the energy we put in per cycle. And we can find that E is equal to work over Q sub H. And for any engine, this is always less than 1 because there's no perfect engine. Now, for a Carnot engine, which is considered the most efficient engine, we find that the efficiency of a Carnot engine is equal to Q hot minus Q cold over Q hot. and that becomes 1 minus Q cold absolute value over Q hot. And we also find that's equal to T hot minus T cold over T hot, which is equal to 1 minus T cold over T hot. So these are ways of finding the efficiency of an engine. And many problems will say such and such an engine has an efficiency equal to 50% of a Carnot engine. So you could use these values to calculate the efficiency if it was a Carnot engine, and then take the 50% of that as was stated in the problem. And since efficiency is a ratio, there are no units to it. No real engine can have an efficiency greater than the efficiency of a Carnot engine. If it is equal to the efficiency of a Carnot engine, then basically it is a Carnot engine. And E, the efficiency, can never equal 1. There are no perfect engines, and we can restate the second law as an engine law as follows. This states that no process is possible where the sole result is the transfer of energy as heat that is completely converted to do work. So if you go back to our energy transfer diagram way up here, you can see that some of the energy goes into doing work. There always has to be a loss of heat. You can't have all the energy going into work. That will violate the laws of entropy and is impossible. Now let's discuss refrigerators, which are basically heat engines in reverse. A refrigerator does work to transfer energy from a lower temperature reservoir, mainly the inside of your refrigerator, to a higher temperature reservoir, which is basically the air in the room. And this would include air conditioners and heat pumps. So you can see the energy flow diagram here, and you can see work being done to pull energy or heat from the cold reservoir, TC, and bringing that up to the hot reservoir, which would be room air. So we calculate the efficiency of a refrigerator using something called the coefficient of performance. And that's given by the letter K. So K is equal to the energy removed by the refrigerator divided by the energy put in to get the refrigerator to work. So we can calculate K as Q sub C over work done, which is equal to Q sub C over Q sub H minus Q sub C. And again, for a Carnot refrigerator, we can get the coefficient of performance sub C equal to TC over TH minus TC, which is also equal to QC over W. So we can restate the second law again for refrigerators, such as a refrigerator second law, and that is, it is impossible for any process to have a sole result that the transverse heat is from a colder body to a warmer body. That is, without doing work on the system. Now let's look at the statistics of entropy. We'll assume the free expansion of an ideal gas, and we'll look at the configuration of the molecules. Although the molecules are identical, we will consider each of them as having a separate configuration, or microstate. And let's talk about gas molecules distributed in a container holding the gas. And let's start with the gas molecules in each half of the container. So the number of microstates that are possible, the configurations of each individual molecule that are possible in that container, is given by W equals n factorial over n1 factorial times n2 factorial, where n is equal to the total number of molecules in the container, and n1 and n2 is equal to the number of molecules in each half of the container. And W is called the multiplicity of the configuration. In other words, the number of ways the microstates that can be configured, or the number of microstates that are possible. And it's similar to flipping a bunch of coins. Some will land heads up, some will land tails up, and each coin, whether it's head or tails, is one microstate. But we're looking at gas in a container. So we will assume that all microstates are equally probable, but different configurations are not. In other words, different configurations have different numbers of microstates. How many coins would end up heads up? How many tails up? And which ones? So we can relate the multiplicity to the entropy through this equation. Entropy is equal to K times natural log of W, where K is Boltzmann's constant, which we've seen before. And that's equal to 1.38 times 10 to the minus 23rd joules Kelvin. We then find that the change in entropy is equal to K log W2 minus K log W1, or K log W2 divided by W1. Now, sometimes when we look to find the factorial of a large number, such as n factorial, it gets difficult to do so. But we can actually use something called Stirling's approximation to find n factorial. And Stirling's approximation says that log of n factorial is equal to n times the log of n minus n. And this can be used to find n factorial. It turns out that for any thermodynamic process, the most probable macroscopic state is the one with the greatest number of microstates, which is also the macrostate with the greatest randomness and greatest entropy. Let's do some problems. Here's the first one. A piston compresses a gas in a cylinder slowly so that the temperature remains at 20 degrees Celsius, which is an isothermal process. The compression causes 800 joules of work to be done on the gas. What is the change in entropy of the gas? So we know that this is an isothermal process, so the change in temperature is 0. That means the change in internal energy is 0. And from the first law, that's equal to Q minus W. So we end up with Q is equal to W. And in this case, Q is equal to 800 joules. But we're going to use minus 800 joules because the work is being done on the gas, which means the gas is doing negative work. And we also know that our temperature is 20 degrees Celsius, which is equal to 293 Kelvin. So our formula for change in entropy is equal to Q over T. So that's equal to minus 800 joules over temperature. So our change in entropy ends up being minus 2.73 joules Kelvin. So the entropy is decreasing in this system because the compression is causing the molecules to become more concentrated and more ordered in a smaller volume. However, even though the entropy of the gas is going down, we still have to obey the second law of thermodynamics, which is delta S is greater than or equal to 0. So somewhere else in the system, the entropy is increasing so that this law is still obeyed. Let's do another problem. A steam power plant has an output of 50 megawatts. The steam enters at 500 degrees Celsius and exits at 120 degrees Celsius. The efficiency of the plant is 70% of a Carnot engine. What is the power put into the plant, and what is the power lost during the process? So let's look at our givens. We're given that the high temperature is 500 degrees Celsius, which is equal to 773 kelvins. Our cold temperature is 120 degrees Celsius, which is equal to 393. We're told the power out is equal to 50 megawatts. And we're told that the efficiency of the plant is equal to 70% the efficiency of a Carnot engine. So let's start by getting the efficiency of the plant. So the efficiency of the plant is equal to 0.7 times the efficiency of the Carnot engine, which is 1 minus Tc over Th. So that's equal to 0.7 times 1 minus 393 over 773, which ends up being 0.7 times 1 minus 0.51, which is equal to 0.7 times 0.49. Okay, that's the efficiency of the Carnot engine. So the efficiency of the plant is equal to 0.36. Now we're looking for the power put in to run the plant. So if we say that the power put in times the efficiency will give us the power out. and we were given that as 50 megawatts. So the power in times 0.36 is equal to 50 megawatts, or the power in is equal to 50 divided by 0.36. The power in is equal to 138.9 megawatts. So we were also asked to find what the power lost was. Well, if the efficiency is the power that is useful, then what's left over is the power that's lost. So the power lost is equal to 1 minus the efficiency times the power put in. So in this case, it's equal to 1 minus 0.36 times the power in, which we just found above, 138.9 megawatts. So that's equal to 0.64 times 138.9. So the power lost is equal to 88.9 megawatts. Now, another way you could have found the power lost is that the power lost is equal to the power in minus the power that was used to do work, or the power out. So in this case, the power in we found to be 138.9 megawatts. The power out was given as 50 megawatts. So the power lost, again, comes out to be 88.9 megawatts. So there's two ways you could have found the power lost. Let's do another problem. A cottage in winter is kept warm by a heat engine that takes water in from a lake at 2 degrees Celsius, then extracts the heat until the water almost reaches freezing. It then ejects the water into the outside air, which is at minus 20 degrees Celsius. The efficiency of this heat engine is 1/5 that of a Carnot engine. The energy or work required is 10 kilowatts. At what rate must the water be pumped to the heat engine for this process to happen? The specific heat of water is equal to 4.18 joules per gram degree Celsius. So let's look at our givens again. We know that the hot temperature is 2 degrees Celsius, which is equal to 275 Kelvin. The cold temperature is minus 20 degrees Celsius, which is equal to 253 Kelvin. We know that the heat capacity of water is 4.18 joules per gram degree centigrade, and we were told that the efficiency of our system is equal to 1/5 that of the efficiency of a Carnot engine. So we know that the efficiency of a heat engine is equal to work over QH, and we're given that that's equal to 1/5 of the Carnot engine efficiency, which is given as TH minus TC over TH. Now, in this equation, Q is equal to MC delta T. So if we substitute that in, we get work over MC delta T is equal to TH minus TC over 5TH. And the problem reads that the heat engine takes water in from the lake at 2 degrees Celsius, extracts heat until the water is almost freezing, which is 0 degrees Celsius, then ejects it. So we're going from 2 to 0 degrees Celsius. So our delta T in this case is equal to 2, because we're looking at the change in the temperature of the water itself. So we can put that in as delta T in this equation. Now we're looking for the rate at which the water has to be pumped. So we'll want to find the mass per unit time of the water. So we want to get mass in the numerator, so let's flip this equation. And we get mc delta T over W is equal to 5th over th minus tc. And now let's solve for the mass. So the mass is equal to 5th over th minus tc times W over c delta T. And we're looking for rate, which would be the mass per time, and we'll call that 1 second. So if we then divide by t and divide this by t, which is equal to 1, we get the rate, which is equal to m over t, which is 1 second, is equal to, and we can put the numbers in, 5 times 275 over 275 minus 253 times the work done, which we're given as 10 kilowatts, which is 10 to the 4th watts, divided by C, which is 4.18, times delta T, which is 2. So that rate becomes 1375 by 10 to the 4th over 184, which is equal to 7.5 times 10 to the 4th grams per second, or 75 times 10 to the 3rd grams per second, which is equal to 75 liters per second. So the rate of water flow for this heat engine has to be 75 liters per second. Let's do a refrigeration problem. A freezer has a coefficient of performance of 6. If the temperature inside the freezer is at minus 20 degrees Celsius, what is the temperature of the sink the heat is deposited into? So the coefficient of performance, which is K, which is a measure of efficiency, is equal to 6. And we know the cold temperature is equal to minus 20 degrees Celsius, which is equal to 253 kelvins. And we're asked to find the temperature of the heat sink. Okay, well, we know that K is equal to QC over W, which is equal to TC over TH minus TC. So we know that K is 6 because we were given that. That's equal to TC, which is 253 over TH minus 253. So we solve for TH, and we get 6 times TH is minus 1518 is equal to 253, or 6 TH is equal to 1771, or TH is equal to 295 Kelvin, which is equal to 22 degrees Celsius. We're going to do one more problem involving entropy and multiplicity of states. The probability of the microstates of an ideal gas is similar to the probability of coins in a coin toss. Assume there are 100 coins. If thrown up, the number of ways that only one head will show is 100. Any of the coins can land head up. The number of ways that 50 coins will show up heads is 1 times 10 to the 29th. The coins start on a tray with only one head showing, then are thrown up and come down with 50 heads showing. What is the change in entropy of the coins due to this toss? So we're going from a state where we have one coin heads up to a state where we have 50 coins heads up. So our change in entropy is equal to K times the log W2 over W1. So in this case, W1, the multiplicity in the first state, is equal to 100. We're given that. And we also know that if there are 100 coins, any one of them can be heads up. But W2 we're also given, and that is 1 times 10 to the 29. That's the chance of 50 coins being heads up. So if we plug that in, delta S is equal to, well, K is 1.38 times 10 to the minus 23rd times the log of 10 to the 29th over 100. So that's equal to 1.38 times 10 to the minus 23rd times the log of 10 to the 27th, which is equal to 1.38 times 10 to the minus 23 times 27 times the log of 10, which equals 1.38 times 10 to the minus 23rd times 27 times the natural log of 10 is 2.3. So this equals 85.7 times 10 to the minus 23rd, or let's just say it's equal to 8.6 times 10 to the minus 22 joules Kelvin. That's the change in entropy in going from one coin heads up to 50 coins heads up.